The acceleration due to gravity on any planet is calculated, we get this from Isaac Newton, by this formula. You can calculate this g-force I've been referring to if we know the mass of the planet itself and how big that planet is, its radius, how distance from the surface to the center. And the capital G is Newton's gravitational constant, an exceedingly tiny number, simply due to the fact that we can imagine a couple of sizable objects, a pair of Mack trucks, packed pretty close together, small r, and not really observe a gravitational attraction between them. Is it possible that the planet Krypton, in fact, has a radius smaller than the Earth's? Well, if I look at that formula, the r, the radius, appears at the bottom. It's a denominator, so it represents a number that gets divided into the stuff at the top, the mass. And in fact, if r were a smaller and smaller number, then if you divide by a smaller number, you get a bigger answer. So yeah, maybe Krypton could in fact be a planet smaller than the Earth by radius, if the radius was small enough to make this answer big. Could the mass of Krypton even be less than that of the Earth? Well, again, if the r were compact enough, then I suppose the division by the r, notice, gets squared at the bottom, might make it possible that we could get the big enough g for Krypton with a mighty small r. But of course, clearly, to get a big value of little g, you'd like m to be large, r maybe not so. As soon as I start talking about the mass packed into the girth of the planet, that brings to mind the notion of density, how much material is packed into a given volume. And that's how density is defined, total mass divided by the volume it occupies. And if we're talking about a planet, they're basically spherical. So for the volume, I've put the well-known volume for a sphere, 4/3 pi r cubed. If I go back to my formula for calculating the g-force on the surface of a planet, then the mass could be represented by the volume multiplied by the density. If I take the volume of the planet, multiply by the average density of the stuff inside it, I'll get its total mass. So in place of mass, if I put density times volume, and the volume is 4/3 pi r cubed up here, this simplifies. The r cubed at the top mostly cancels with two of the factors of r at the bottom, and I get this expression, that the force of g on a planet's surface depends upon, round planet, 4/3 pi g r rho, its density. In other words, how big around the planet Krypton needs to be depends upon the density of the stuff that it's made out of. Let's look at some possible candidates of stuff we could pack into that planet, like, the elements. The surface of the Earth is 72% covered, 72% with water, but that's just the surface, right? The volume of the Earth's not filled with water, so the amount of water on the planet is sort of an insignificant sliver of its total mass. Most of the mass is the stuff inside, the solid junk. And you might think solid junk inside the Earth like granite, 2,700 kilograms per cubic meter in density. There's certainly denser stuff like lead and gold, but we don't live on a planet that's solid gold. What do we know about the density of the planet Earth? Well, below the topsoil is the crusty material that we anchor our buildings in, the bedrock. That is like a lot of granite and composition of minerals whose density is very close to it. But in fact, all of the crust added up together, that's this thin little layer here, is barely 0.5% of the total mass of the planet Earth. Most of the Earth is made out of the mantle, the silicates that are about 4 to 5 or 6,000 kilograms per cubic meter in density. There are the inner and outer core, but they're about 15% of the planet's total mass. The Earth is mostly what its mantle is, and the average density of the Earth is very close to the density of its mantle. Interestingly enough, all of the meteorites that we've been able to study seem to have compositions and densities that are extraordinarily like the mantle of the Earth, as if the rocky stuff made in space is not really much different than the rocky stuff the planet Earth is made out of. Here's a list of the planets we know best, namely the ones in our solar system, and their densities. And if you look particularly at the rocky ones, the terrestrial planets, the ones that are Earth-like, they all have average densities that are about the same. Again, reinforcing this idea that perhaps most of the rocky stuff in space is made out of very similar material. Nothing dramatically different. Of course, not all of the planets are that dense. The Jovian planets, the big ones, the ones in the outer part of the solar system, are they more massive or more dense or less dense than the Earth-like planets? All of these numbers, much smaller. Why are these planets, why do they have such small densities? They're not rocky planets at all. They're mostly gaseous planets. So Jupiter, it's not quite a sun, but it's a big ball of gas that has little more than perhaps a rocky core. Strongly suggesting that any solid rocky planet anywhere in the universe is probably built out of stuff like the Earth is built out of. And we would expect all rocky planets to have roughly the same density, 5,500 kilograms per cubic meter or so. If that number's fixed for all planets, then notice the G and the radius are the only two variables left in that expression. And the fact that Krypton has a G-force 47 times greater than the Earth implies that Krypton must be 47 times broader or bigger in girth, in diameter or radius than the Earth is. So 47 scaled up, 47 times the size. Since the volume of a planet depends upon r cubed, its radius, then the mass of Krypton has got to be over 100,000 times more massive than the Earth. Okay, so we've decided the mass of Krypton is 100,000 times more massive than the Earth, with a radius a little less than 50 times greater than the Earth. Let's see where it would fall and what planet it might most look like of the ones that we know. Okay, 6 times 10 to 29. It is, in mass, about a third of the mass of the Sun. And it's, what, 300 times bigger than Jupiter. In mass, it has to be a planet that's 300 times bigger than Jupiter. And in its radius, it's about a third of the size of the Sun. This is one big whopping planet. I'll remind you that the only rocky planet examples, though, that we've seen have this kind of density and are rather modest in size. Where the big whopping planets, though, like these Jovian planets, are not rocky planets at all. They're gaseous planets. Why is that? Well, one reason is Roche's limit. The further you get away from the source of a gravitational field, like further away you are from the Sun, the weaker is its pull. So the force of gravity drops with distance, in a way suggested by this curve. I've plotted a few data points. As you move away from the Sun, the force that the Sun pushes with you drops dramatically. Imagine placing some large planet in orbit about the Sun. By large, I mean large enough, and I was talking about something that had to be really large when I was talking about Krypton, so that its near side and far side are surfaces of drastically different distances from the Sun. That means the front-facing side of this planet is pulled much harder toward the Sun than the back side. It would be as if it were trying to force the near side of that planet to orbit a little faster than the back side. Now, if the difference in that force is, you could say, oh, it's a solid planet, so what? It's going to move as a solid body. Not if these forces are different enough that they exceed the force with which rock can hold itself together. If the planet is big enough, there's no guarantee that that'll be so. The results are known as tidal forces, which would tear such a planet asunder, and is in fact our best explanation for the rings that exist around ringed planets. Moons can't form in certain bands around that planet. They're too close for any rock of any substantial size to start to accrete. It also explains the existence of the asteroid belt. Interestingly enough, for a long time it was speculated the asteroid belt were remnants of an exploded planet. And that was in fact the inspiration for Krypton. And maybe that was Krypton at one time, was the idea. A planet that's simply too large for the Roche's limit of its star is unstable and definitely would be in the danger of fragmenting. But I'll remind you that the biggest planets are all gaseous planets. That's confirmed by spectral analysis. Studying the light reflected off those planetary surfaces tell us something about the composition and the state of the matter on that planet. They're all mostly balls of gases. The most massive planets also, early in their formation, have gravities that are strong enough to hold on to their atmospheric hydrogen and helium during their formation, unlike, for example, planet Earth. That means probably all really, really, really big planets in the universe are all destined to be gas giants, not rocky planets at all. So could Krypton ever have even existed? Hey, maybe. The remnants of a collapsed star that has gone supernova is matter that gets crushed into such an exotic and dense state that the separate existence of electrons and protons are replaced by only neutrons. This nuclear state, denser than the nuclei of atoms, is such that you could imagine a planet nearly 50% bigger than our own sun, not expanding beyond the boundaries of the city of Lincoln. And a teaspoon of such nuclear matter would weigh 10 million tons. Perhaps, with those sorts of densities, you could imagine a planet with an exotic origin seated in a gaseous cloud by a fragment of nuclear matter that condenses into a planet. In that case, an almost insignificant amount of nuclear matter could produce an Earth-sized planet that did indeed have 47 times the Earth's gravity. And boy, if it had nuclear matter at its core, which often the original comic suggested, that planet would definitely be unstable. So, if there were a race of supermen that had evolved on a planet with 47 times the intensity of gravity as here, yeah, I think they could leap tall buildings in a single bound here on Earth, jump an eighth of a mile in a single stride. And even better than that, having evolved under Krypton's enormous gravity, be able to lift giant weights. Here's Superman uprooting a tree. There he is tossing an armored car around. I found this image online from some, I think, Arabic comic. I have no idea what they're saying, but I bet it's a really good elephant joke. An athletically fit man, most of us, can bench press about 1.5 times their own weight. And so for a 225-pound Superman with 47 times as strong of muscles, he probably should be able to lift, bench press, all that stuff like 7 or 8 tons. So let's go down the checklist of things he supposedly can do. Yeah, he can toss a car, a sedan, a minivan, an SUV, even an elephant around. But a school bus? Well, if I hadn't seen it with my own eyes,